Hello guys, I will show you how to make an infinite hexagon. And no, it is not infinite. It is not infinite in the way that you could conventionally say it, I guess. There's a limited amount of um, inputs or sets or whatever you want to call them. This set can be defined as any real number are, I guess. I guess that's what real numbers are, except negatives. No negatives. I hate negatives, especially in geometry. So I'll show you. What I mean by this is, imagine the idea of 6 lines and they go on to infinity. How would that create a pattern of hexagons? Well, I will show you. Hexagons are made up of 60 degrees. They're a triangle that is made up of 60 degrees, an equilateral triangle. And well, that's 60 degrees, but we don't want to close it. We don't want a shape. We want an open shape. So that goes on to infinity. You can't make an infinity out of a closed shape. So I mean, you probably could. So let's draw that. Let's start with 2 lines. 1, 2. This angle and this angle must be equal. And well, if we did things right, this should be 60. But I'm just eyeballing it here. These are 60 and this is 60, right? And this obviously is not a hexagon, so we know already that this angle must be, well, 180. It's the end of the line, right? So it should be, well, a line. It adds up to 180 angles, and you subtract by 60, you get 120. So this angle is 120. That's pretty good for what we want, because that means we can divide this by 2. We can cut this in half. We cut this in half. Damn it. Whatever. We cut it in half. Where's the eraser? We cut this in half, and now we just have a plane of lines. But this isn't a hexagon, right? I will show you. Imagine a perfect circle somewhere, anywhere. But for now, I'm gonna draw it like, I'm gonna draw this a little bit larger. Now, make it go a little bit further into the infinity. And well, how does this make a hexagon? Of course, it has like 3 open angles, 3 open sides, like it's not closed. A hexagon is a closed shape, equilateral, you know? Well, what else is equal on all sides? Like, not a hexagon. It's not equal on every side. Like, it's made up of these shapes, right? You know, 60, 60, 60, right? X is equal, X is equal, X is equal. But what is not equal is this, the length. So, you know, the only way to find the length is to x divided by 2, x squared divided by 2 plus L squared equals x squared. That's how you'd find the length of this. But doing this operation on a, you know, if x is given, and well, you can find out what the length is, and the length is not 6. It's close to 6, but it's not. So we want a shape that is equal on all sides, a shape that has equal radius on all sides, you know, length to the edge, and that is a circle. So we will do that. This is a pretty bad circle, but what we do now have is intercepts. 1 intercept, 2 intercept, 3 intercept, yeah, a bunch of them. Draw circles. These are your points. These are your points of the hexagon. You don't need sin for any of this. I saw you, Kyle, do something like this. You do not need to do that. All you need to know is to know the constant increase of the hexagon, which is a given because every hexagon is similar to each other and related, sort of like a family, I guess. If it's equilateral, it will have the same rise and run. So let's say Let's say the circle's radius is 3. Well, we know since this must be 3 too, since x is equal to, well, all these sides are equal to each other, so we know that this would also be 3, this would be 3, so on. I'm getting a little bit ahead, but let's this is still an open shape, so let's connect the dots. The rule about this game is you can only connect adjacent things, and you gotta start somewhere, right? So we shall connect adjacent sides. Bam, 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 and bam. What an amazing hexagon. If we did this in an actual plane, you'd come to find that this would create a perfect hexagon. What does this say about our hexagons or any equilateral shape? It says that these slopes are constant. The only difference is the orientation, and the orientation is relative. Space itself is relative. We don't have an x and y value. The universe might have an x or y graph like this, like a quadrant. It might not. It probably won't. But it's all relative. We don't know that point A is actually, you know, one metric unit away from B. We just use like some stupid way of like finding distance, like, feet. Like, who would actually use actual feet? Like, you know, it's all relative. Our way of understanding the world is relative to ourselves, to things we can see. That's why whole numbers existed longer than decimals, fractions, because for a while, well, you had an apple, you had two apples. If you cut that apple in half, well, you have one apple. It worked simply back then, but once you cut one in half, then what are you left with? Half. Well, anyways, it's all relative. You could rotate this all you want. You won't. All you'll be able to know from the only way you'll know and where the orientation of any two spots is if you have like two given spots, I guess, because it might all be relative, but it follows a certain pattern. Let's erase all of this. Darn, I don't know how to erase this all. Let's make another game. I don't know. Imagine this. Okay, we got the same points. We got the same points. I don't need to remind you we have the same points. Alright, so let's do this again. This, this, 60, 60, 60, 60, 60. Alright, this is 60, this is 60, this is 60, whatever. Draw a circle again this time. And draw a circle where your points intersect. Now, let's change the rules of the game. Okay, instead of going to adjacent spots, go to opposite spots. Draw a line from opposite to like maybe something that's not adjacent. It doesn't matter. As long as it's not next to you, you can connect the dots. You can connect the lines. It doesn't matter. But what you absolutely cannot have, or else this whole thing fails, is or at least it won't fail. You'll still have the points. You'll still have the line. If that's your goal, to have lines, then you've gotten it. But say your goal is to have a closed shape, you'll fail, and I will show you why. So let's start off. Let's go here. Okay, connected to you. 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 Connected to you. And then connected to you. Like, this is not a closed shape. You can't do this. It's not closed anymore. And I will show you, like, there's certain shapes that can like be closed when not going to adjacent, dots. Let me show you. So a hexagon, no, a pentagon. You see those little stupid stars that your teachers used to give you in middle school, right? They'd give it to you like, oh man, you did a great job, feeds your ego, right? So imagine this. Okay, I'm gonna draw the points just to be fast. Let's see, 1, 2, 3, 4, and 5. Now draw to opposite points. 1, 2, 3, 4, 5. 5 lines. You could easily do it. You can only draw 5 lines. This hexagon, like, you can only draw as many lines as the sides, and a hexagon does not do this. Let's try and do this again. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. It fails the game every single time. And this is a weird pattern you can see. As long as it's odd, or as long as it's odd, you can connect it like this. But you cannot connect it, there's a certain way you can't connect these. I forgot it, but that's a unique property of these kinds of shapes. And, you know, think of hexagons, think of all these shapes as like lines in an infinite plane that you could sort of just find, you know, a relationship to, because these are all linear. These are linear. They got lines, and these lines will be consistent to each other. Or not consistent to each other. They will be consistent. They will follow the same pattern of the circle and the bunch of lines. They will always follow it without fail, as long as they're equilateral and as long as the intersection points are where you want them to be. Like, this is what I'm saying, okay? The hexagons are beautiful, and that's what you should get out of this. And if you don't get out of this, then you're dumb, and you should drop out of high school instantly. Okay? Bye.